Hello and welcome to my channel. In today's video, we are going to be solving our LC circuit problem that involve the calculations of inductive reactance and we are also going to be solving the capacitive reactance and as well as the impedance. After that, we are going to solve the voltage across each of these components. So what is the RLC circuit? The RLC circuit, it is a circuit in this form where you have a resistor connecting. You also have an inductor connecting to the same circuit, and you have a capacitor connected to as well. This is a power source and it is AC power source. It is not necessary for it to be AC power source, but this problem is what I have just decided to use the AC power source in this case, right? So this is the resistor and this is the inductor. The symbol is L and this is a capacitor, right? Let's try to understand the functionality of each of these components. As for the resistor, the main purpose of the resistor is to reduce the voltage across the circuit. Let's say, for instance, if you have 10 volts as the input that is going within the circuit, and you have 10 ohm, right? And the equation for finding the voltage is just the current times the resistance. So trying to figure out your current, you're going to have the equation R is equal to V over R. So the resistor value is going to be decreasing the voltage here, and as the voltage is decreasing, the current is also decreasing as well, right? So the current is inversely proportional to the resistance here. So as the resistor value is increasing, the current is also decreasing. As the voltage is increasing, the current is increasing. So that's how it goes. So in this problem, like we have R here, we're gonna have 1 ohm as the value of I. 1 ohm here. So as you increase this value, we also want to have a decreased voltage here, and the decreased voltage will also decrease the current too as well. Right? So as for this inductor, the primary purpose of an inductor is to prevent the sudden change in the current across the circuit. Basically, when the AC voltage is applied to an inductor, the current through it lags behind the voltage by 90 degrees. So this lagging current creates a magnetic field around the inductor, right? So when the voltage across the inductor decreases, the stored energy is released back into the circuit by the inductance. So due to that, the voltage across the inductor here is going to be larger than the voltage that is entering within the circuit. So we are going to be solving that problem, and we're going to see the voltage across the inductor and the capacitor is going to be larger than the input voltage. For the capacitor, it would tend to prevent the voltage changes within the circuit too as well. So let's get started by solving some of the problem. For the inductive reactance, we have the equation X L is going to be 2 pi F L here. So this is the equation for this inductive reactance. So let's assign some value to this circuit. For For this circuit here, we have, let's say, it's 120 volt AC, right? This sign stands for AC, and it is 50 hertz, and the value of this inductor, let's say, is 0.15 Henry, since the unit is Henry, and the capacitor here, let's say, is 100 microfarad. And for the resistor here, let's say the value of the resistor here is 12 ohm. So the next thing is to try to figure out how can we deal with different components of this circuit. As you can see, a resistor, this is resistor, and the property of this resistor is a resistance. We cannot add a resistance to reactance. So inductor and a capacitor, they are all reactance, and we cannot add them. The reason why we cannot add them is that the reactance here is a real value or a real number, while for these two, they are just imaginary, all right, or complex value. It is in this form: Z is equal to A plus BI, right? It's just the simple algebra. So this portion here is the real part, while this portion is the imaginary part. All right? So this portion is going to be represented by this 2, and this portion is also going to be substituted instead of the A here. So substituting the value here, we're going to have Z is equal to R here plus this, we call this JX, right? Because I don't want us to confuse this I with current in the future. So since we're going to be solving for the current, let us use J instead. All right, so now we have Z is equal to R plus JX, and this X is the inductive reactance and also the capacitive reactance here. So substituting the value for X here, we're going to have the inductive reactance minus the inductive capacitance. So this is one of the equation, and it is an equation in the polar form. So this is the polar form of impedance, and this Z here stands for impedance. Impedance. It is used whenever we decide to sum this value. The equations for impedance here is Z is equal to the resistor square here plus the difference between these two, XL minus XC square them, right? So this is the equation that we're going to be using to calculate our impedance, right? So next, let's try to calculate the impedance here. Before we calculate this impedance, let us try to calculate the inductive reactance and that of the capacitive reactance. The inductive reactance is given by this formula, as we said, right? So substituting the value for inductive reactance here, we have 2 pi, and frequency is 50 hertz. We're given the 50 hertz here, and multiplying that by the value of the inductor here, which is 0.15. All right, so this is going to give us 47 47.12, right, ohms. They are all measured in ohm. So the next one is to solve for the capacitive reactance too as well. As for the capacitive reactance, we are going to express it on the 1. Here it's going to be the same equation, 2 pi frequency. Instead of L here, we're going to use C, and C is the value of the capacitor here. So XC is then equal to 2 pi, the frequency is 50, and the value of the capacitor here is 100. Since it is microfarad, we are going to convert that to farad. That is 10 to the minus 6. So plugging this into the calculator, we're going to have 31.83. There was an error here. So now that we have these two values, we can go ahead by calculating our impedance here. So going ahead to calculate our impedance, we're going to have Z is equal to the resistor value, which is 12, square that, plus the difference between these two. First one is this is one we're going to start it from, 47.12, subtracting 31.83 from that square. So plugging this into the calculator, we will have 19.4 ohms. Right? Now that we have this impedance here, in the exam, sometimes you might be asked to find the voltage across this component. So finding the voltage across this component, we should know that voltage is equal to R. And in this case, we have an inductor and a capacitor, so we're not going to use this R instead. So this R here is going to be replaced with Z, since here is the combinations of these reactance and resistance. Alright, so in this case we're going to have V is equal to RZ. So solving for I in this equation, we're going to have R is equal to V over Z. Right? Good. So now this equation, let's bring it here. R here is going to be V. The value of V here is the voltage that is entering within the circuit. So the voltage that entering within the circuit is 120, dividing that by the impedance value, which is 19.4 volt ohms here. This is going to give us 5.15 right? So now the voltage across this resistor is going to be the current across this circuit here, which is this. So the current across this circuit, since they are all connected in series, is going to be the same current across all of these components. All right, so we are going to use this current to calculate the voltage across all of these components, since they are all connected in series. So in this case, the voltage across this resistor here is going to be say V R here is going to be this current times the value of the resistor. So in this case, we have VR is equal to 5.15 times 12. This is going to give us 61.8 volt. Right? And the next one is this. It's going to be VR, which is the inductor. Now, in the reactance of the inductor here, we already saw for that, and it is 47.12. So we're going to multiply that by x1. So it's going to be XL here. So the voltage across the inductor is going to be the current 5.15 times the X area, which is 47.12. So V error here is going to be 242.5 volt. So now we do the same for VC, which is going to be IXC, right? And we already have a value for XC too. So solving this equation, we're going to have 5.15 times 31.83. So VC is going to be, in this case, 163.9 volt. Notice that if you sum all of these voltages, it's going to be larger than the voltage that is entering here, right? As you can see, this is 163 volt that is across the capacitive reactance here, and it is larger than the input voltage. What is going to happen here is that when the current is going across the circuit, the inductor is going to store energy. So as a result, when the voltage is decreasing, the stored energy is going to get released, resulting in the increase of the voltage across the circuit. So the same thing applies for this one, for the voltage as well. So to confirm that this 120 volt is equivalent to these voltages, we use this equation. It is the same equation that we use for impedance here, but this time around, instead of substituting the value for resistance and this one, we are going to substitute the voltages across this resistor. So in this case, we have, I've just made some slight changes in the voltage here. At first it was 120, but now I've changed it to 100. It is the same. I first performed the calculation and it is the same value. So now to confirm that you have 100 voltage entering within the circuit, we are going to use this same equation here and plug in the value of the voltage across the reactance and also the voltage across the resistor here. We end up getting the same 100 volt, right? So this is to prove that the voltage across this reactance and resistance is equal to the voltage that is entering within the circuit. So thank you very much for watching this video. I'll see you in the next video. Bye.